Okay, we continue to learn Chapter 3, Vector Spaces. Section 3, Linear Independence. And Part 4, Linear Independence and Dependence in Pn and Cn-1 AB in these two functional vector space. Okay. Vector space of functions. The properties of linear independency can be adjusted to vector spaces of functional as well. So in order to test whether the polynomials P1, P2 till Pk are linearly independent in Pn, we also set this type of equations. So it is C1 times P1 plus C2 times P2 plus till plus Ck times Pk equals 0. Because P1, P2 till Pk are polynomials of degree smaller than n, less than n, so eventually you can transform the left side to this term, this type, like a1 times x power n minus 1 plus a2 times x power n minus 2 plus till plus a n minus 1 times x plus a n equals 0 for any x. So if you find this one equals 0, then it is equivalent to require a1 equals a2 equals till equals an equals 0. Okay, and because each ai is a linear combination of the ci's, which leads to a homogeneous linear system with unknowns c1, c2 till ck. So the system has only trivial solution if polynomials are linearly independent. So example, ask you to test whether the vectors P1x equals x power 2 minus 2x plus 3, P2x equals 2x power 2 plus x plus 8, and P3x equals x power 2 plus 8 times x plus 7 are linearly independent or not. So just see its requirement is relating to linearly independence or linearly dependence. So immediately consider about the equation equals 0. Which equation? So it is C1 times P1 of x plus C2 times P2 of x plus C3 times P3 of x equals 0. And then write the left side as a combination of the x power 2 term and the plus x power 1 term plus the x power 0 term. Okay, this one equals 0. And this one equals 0 if and only if all the coefficients are relating to C1, C2, C3 are 0. So you will get also a homogeneous linear system and solve this linear system. And then you can get the solution, get the answer. You can find non-trivial solution, then they are linearly dependent. Otherwise, they are linearly independent. Okay, you can try this later. Okay. Now we consider this vector space Cn-1 AB. So this space contains all the functions in closed interval a to b, where the function has a continuous n-1 derivative. Okay. Let f1, f2 till fn be elements of this vector space. Decide whether this set of n vectors is linearly independent. If these vectors are linearly dependent, then there exists scalars C1, C2 till Cn, not all 0, such that these equations hold for each x, for any x in the closed interval a to b. Right? And continue taking derivatives of both sides, you will get this is the original equation, the linear combination of these given vectors f1, f2 till fn, where each vector now is a function. Okay, it's a continuous n-1 derivative is continuous, this function. Okay, and then you do the first derivative, you will get c1 f1 derivative of x plus c2 times f2 derivative of x plus till plus cn times fn derivative of x equals 0. And because they have n-1 continuously derivative, so you do this derivative until this term, until this one. So it's C1 times F1 is n minus 1's derivative plus C2 times F2 is n minus 1's derivative plus still plus Cn times Fn is n minus 1's derivative equals 0. Okay, to see this system, okay, we immediately note that for each fixed x in this closed interval a to b, the equations will have the same non-trivial solution if f1, f2 till fn are linearly dependent. The linearly dependent means that you can find a non-trivial solution C1, C2 till Cn such that this first equation holds, and if the first equation holds, immediately you have the second equation holds until the last one. So if this system has the same non-trivial solution, then it is possible f1, f2 till fn are linearly dependent for every x in closed interval a to b. Remember this, okay? So this is a strong restriction, right? For each x in this closed interval, if they are linearly dependent, the system has the same non-trivial solution. Each equation has the same non-trivial solution. Okay, now if f1, f2 till fn are linearly dependent, then the coefficient matrix is singular for each fixed x in a to b, closed interval a to b. If f1, f2 till fn are linearly dependent, then the determinant of the coefficient matrix is identically 0 on this closed interval a to b. See? So if it's linearly dependent, you will find the determinant of the coefficient matrix with respect to any x on this closed interval is 0. If the determinant of the coefficient is not identically 0 on this closed interval, then you must have f1, f2 till fn are linearly independent, right? If it's linearly dependent, they must be identically 0 for any x on closed interval a to b. And as long as you find one special x0 such that the coefficient matrix is not 0, then the functions, the vectors in this vector space, they are linearly independent. Okay. If there exists a point x0 belong to closed interval a to b such that the determinant is not 0, then these vectors must be linearly independent. Okay. Now we give this definition. Let f1, f2 till fn be functions in this vector space, and define the function w f1, f2 till fn x on AB by this form. See, we just write the coefficient of this system. See, this system, the coefficient of this system as a matrix, and in fact, it is a square matrix. It has n rows and n columns. So we just write this matrix and we compute its determinant. And this determinant should be a function, right? Should be a function. And the function, we give a name. We call it the Wronski of f1, f2 till fn. So by the analysis before, we can have this theorem that f1, f2 till fn be elements of this vector space if there exists a point x0 in the interval, closed interval a to b, such that its Wronski at x0 does not equal to 0, not identically 0. This means the vectors f1, f2 till fn, they are linearly independent, right? Because if they are linearly dependent, they should be identically 0 for every point in the closed interval a to b. Now you find one which is non-zero, so they are linearly independent. So this Wronski is for determine is linearly independent. It's an efficient way to determine it's linearly independent. Okay. For example, ask you to show that e power x and e minus x are linearly independent in this vector space, say minus infinity to infinity. So this one should be a continuous function, right? Continuous function on this interval minus infinity to infinity. Okay, and we compute its Wronskian. Okay, its Wronskian as the first row is ex e minus x. The second row is its derivative. The derivative of ex is ex itself, and the derivative of e minus x is minus e minus x. And then you compute its determinant, you find it's minus 2. If it is minus 2, the Wronskian is non-zero at any x in this closed interval. Then, of course, these two vectors, they are linearly independent, right? So to judge it's linearly independent, the Wronskian is non-zero, is very efficient, is very useful. And we should emphasize that if the Wronskian equals 0 on this closed interval a to b, we do not have a conclusion on the linear dependency or independency of f1 till fn, right? Because we only know that if they are linearly dependent, then this one equals 0 for every point on a to b, closed interval a to b. However, on the contrary, on the other side, if this Wronskian equals 0 on the whole interval a to b, we cannot say they are linearly dependent, or we cannot say they are linearly independent. We can take this example, okay? We consider the two functions. One is x power 2, the other one is x times the absolute value of x. Those two functions are vectors in C1 minus 1, 1. So their derivative is continuous on the closed interval minus 1, 1. And if you do the Wronskian, the first function is x power 2, the second one is x times its absolute value, and you do the derivative, x power 2, its derivative is 2 times x. This function, x times absolute value, its derivative is 2 times x absolute value. And you can check this determinant always 0, identically 0 for any x on this closed interval. So can we say these two functions are linearly dependent or linearly independent? So we cannot see from here, right? Okay, now we consider the vector space Cn minus 1 AB. This space contains all the functions that has a continuous n minus 1 derivative. In order to check whether x power 2 and x times its absolute value, these two functions, they are linearly independent or not, we still need the definition from the definition. So we check this equation, C1 times x power 2 plus C2 times x times its absolute value equals 0 for all x in this closed interval, and we can substitute arbitrary x in this closed interval. Here we choose x equals 1 and x equals minus 1. So if x equals 1, we substitute here, you will get C1 plus C2 equals 0. And if you choose x equals minus 1, you will get C1 minus C2 equals 0. Okay, so these two equations immediately tells us C1 equals C2 equals 0. The only way it holds should be a trivial solution, C1 equals C2 equals 0. Therefore, these two functions, these two vectors in this space are linearly independent, although its Wronskian is identically 0. So the Wronskian is identically 0 does not mean these vectors, they are linearly dependent. Okay, we can only say that at some point, if the Wronskian is not 0, then the vectors, they are linearly independent.